In this lecture, we are going to show an stability theorem. We are going to see that some properties that we already know, like being an immersion, a submersion, an embedding, a local diffeomorphism, are actually preserved under small perturbations. Indeed, this is the precise theorem that we are going to show in this lecture. The properties that are listed are stable in the space of differentiable maps from a compact manifold M to a manifold N that is not necessarily compact. And those properties are being an immersion, a submersion, a local diffeomorphism, a map that is transversal to a fixed closed submanifold of the target manifold, an embedding, or a diffeomorphism. What is it going to be the approach that we are going to use in order to show these results? In all cases, we are going to consider a map, F0, a differentiable map that satisfies the property. Okay, in the first case, this property is going to be being an immersion, but it can be any of the other ones. And then we are going to consider a differentiable homotopy. Okay, sorry, a differentiable homotopy such that the f capital F applied to x0 is f0 of x for every x in the manifold. And what we want to show in all of these cases, okay, our goal is actually that the map ft from M to N also satisfies the property, but obviously it satisfies the property if t is actually near 0. So that's the approach that we are going to follow in all of these cases with all of these properties. Let's consider first the case of immersions and also the case of submersions. What happens here? We can consider, given a, okay, what happens in these cases is that if we have F0, a differentiable map from M to N, the property of being an immersion or a submersion is actually can be interpreted in a similar way in both cases. Because if we consider x being a point of M and f0 of x is obviously a point of N, now we can consider a local chart that contains the point x. It's a local chart of M, and we can consider also a local chart, and here W contains the point f0 of x, and C psi is a local chart of N. And what's going to happen is that we can consider the Jacobian matrix at phi of x of the expression of f0 in local charts, which is this one. Right? But if we consider this as a matrix, actually, if capital M has dimension m, small m, and big N has dimension small n, we can interpret this differential as n times m matrix, right? And what does it mean to be an immersion at x or a submersion at the point x? It means that this matrix has maximal rank, right? So F is an immersion if, so F is an immersion at the point x if and only if m is less or equal than n and the matrix of the local expression of F0 in local charts is actually a matrix of maximal rank. And this maximal rank, of course, is equal to m. But being a submersion has a similar characterization. F is a submersion at the point x if and only if m is greater or equal than n, and we have this property over here. Okay? So essentially, both properties can be characterized in terms of the properties of the Jacobian matrix, okay? And the property is that the Jacobian matrix at the point phi of x has maximal rank. But let's actually remind ourselves of a fact that holds for matrices, and it's that matrices of maximal rank are an open set. If you consider the subset of the n times m matrices consisting of matrices of maximal rank, that subset is actually an open subset of matrices, right? And now we have what we need in order to show that the property of being an immersion is an open property. Because as we said, F is an immersion at the point x if and only if we have the Jacobian matrix at the point phi of x of the local expression of F0 has maximal rank. Okay? But since this property is an open property in the set of matrices, that implies that if F is actually an immersion at the point x, then we're going to deduce that Ft is an immersion at the point x prime for every x prime in U and T that belongs to some closed interval whose ends are 0 and delta sub x. Okay? Where okay, for some U that is a neighborhood of x and some delta sub x that is positive. right? So we are actually showing that ft is an immersion at a neighborhood of x for every small delta. And now we can use that M is compact, right? So since M is compact, that implies that Ft is an immersion for every t sufficiently close to zero, okay? For every t in the interval, in the closed interval 0 delta and some positive delta. The proof for the case of submersions is the same, because if f is a submersion at x, then the Jacobian has maximum rank, and what we have to use is this Jacobians vary continuously. That's where we are using that the homotopy is differentiable. It's just there. And so since these Jacobians vary continuously, and the property of having maximum rank defines an open set, then in particular, that's going to imply that Ft is going to be a submersion at x prime for every x prime in a neighborhood of x and for every t sufficiently close to zero. And in the same way that we actually used for immersions by using compactness of M, we get that Ft is a submersion for every t in a neighborhood of zero, whenever F0 is a submersion, of course. Okay, we are actually trying to show that if some property holds for some map, then it holds also for the maps in a neighborhood of this one. So we showed the result for immersions and submersions. We can consider now, for instance, local diffeomorphisms. But local diffeomorphisms are simple because what it is a local diffeomorphism is just it's a differentiable map from M to N in which these two manifolds have the same dimension, and besides that, the map F is an immersion. But obviously, we already proved that immersions, the property of being an immersion is stable. So the property of being a local diffeomorphism is also going to be stable, right? The next property that we want to treat now is the property for a map of being transverse to a submanifold. Okay, let's consider this picture that we used to relate the properties of transversality to submersions. Okay, so what we have is that if F0 is a differentiable map from M to N, and F0 is transversal to the submanifold C of N, what we can consider actually is the set K, which is the preimage by F0 of C. We have to remind ourselves that C is not just a submanifold. C is, by hypothesis, a closed submanifold. Okay, since C is closed, the preimage of C by the map F0 is going to be the preimage of a closed set by a continuous map, and so it's going to be closed. Right? But now we have that K is a closed subset of M. And M is compact. And so a closed subset of a compact set is still compact. So using the compactness of M, we get that K is compact. Now, if we have a point in K, say X is a point in K, we can consider Y as the image by F0 of the point X, and we can actually consider the construction over here. There exists a submersion G, which is going to be defined in a neighborhood of Y in N, and whose target space is RL, where L is the codimension of C. This is a submersion such that the preimage of 0 is going to be C. Indeed, what we can do over here in order to make this clearer is consider W, which is going to be an open subset of N. And here we have this. The preimage of 0 is going to be the intersection of C and W, right? And what happens is that since F is transversal to C, that implies that the composition of G and F is a submersion at the point X. We were considering a point X in K, right? But if this happens, then we have the composition is also a submersion. That here is F0, of course. But if this happens, the composition of Ft and G is going to be a submersion at, I don't know, some open set. For instance, what letter can we use here? U, for instance, at U for any t very close to 0. And again, some neighborhood U of X and delta positive number. So that's the situation that we get because being a submersion is a stable property. And so in this way, by using again compactness, in this case the compactness of K, we can actually see that Ft is going to be transversal to C if T is near 0. And so, in this way, we can prove that the fact that a map is transversal to a fixed closed submanifold is a stable property. Okay? There are two other properties that we have to consider. We have still to prove that being an embedding is a stable property, and also that being a diffeomorphism is stable. Okay? Let us consider first embeddings. So consider for a minute our differentiable homotopy, okay? And we can associate to this map, capital F, another map, which is going to be hat capital F, which is going to be defined in m times the closed interval, 0, 1, and whose target space is going to be n times the closed interval. And that sends xt to capital F applied to xt, t. This map is obviously differentiable. Okay, what we want now is considering the differential of this new map at a point of the form x0. For instance, in local coordinates. In local coordinates, this is going to give us a matrix, and this matrix is going to have a last line, which is going to consist of zeros, and finally 1. And what the other entries of the matrix are not difficult to understand. Here we have the differential of f at x, and here we have some elements that we don't know very well. Okay? What happens is that since f0 in particular is an embedding, okay, because we are assuming that it's an embedding and we want to show that ft is also an embedding if t is close to 0. In particular, f0 being an embedding, it's also an immersion. And this implies that the columns of this matrix over there are actually independent. So when we add this column over here, since all the coefficients in this last line except the last one are equal to 0, then we get that all the columns of this matrix are linearly independent. So in particular, that implies that hat capital F is an immersion at the point x0. But, okay, it's an immersion at the point x0. And in particular, what we get in this situation is that this map is going to be injective in the neighborhood of x0. So, hat capital F is injective in some neighborhood of the point x0. That can actually be proved, for instance, by using the local normal form of immersions. Right. So now we want to show that being embedding is stable. This was something that we needed to do in order to complete the proof. Okay. So what we have is that f0, is an embedding. And as we said, if it's an embedding, it's an immersion, and being an immersion is stable. So that implies that ft is an immersion if t is near 0, right? But we have something else, is that all these maps ft are indeed proper, because all these maps, if, indeed any map, if you have a map from M to N, this map is going to be proper, provided, of course, it's continuous. But this map is proper because the preimage of a compact set is in particular the preimage of a closed set. The preimage of a closed set, because the map is continuous, is closed, but a closed subset of a compact set is compact. So all indeed what we are just saying is that maps defined in a compact manifold are indeed necessarily proper. So in particular, that implies that Ft is a proper immersion if T is near zero. But in a previous lecture, we proved that if we have an injective proper immersion, it is always an embedding. So we need to show that Ft is injective if T is near zero. That's what we need to prove. Okay, so let's go. Suppose it's not. Suppose it's not true that Ft is injective if T is in a neighborhood of zero. Okay, so that implies in particular that given a natural number, there exists Tn that belongs to the interval, to closed interval, whose ends are 0 and 1 over n, such that f Tn is non-injective, right? But if this happens, then we have that there are points xn and yn that belong to the manifold M, and they are different, of course, such that f Tn applies to xn is equal to f Tn applied to yn, right? Now, what we have is that up to consider a subsequence, we can suppose that the limit of the following sequences exist. Okay. The first limit would be the limit when n goes to infinity of xn Tn, and the second limit would be the limit when n tends to infinity of yn Tn. Of course, the second component here is 0 because Tn tends to 0. And what we want to see is that we are going to get a contradiction with the property that we showed about the map had capital F being actually locally injective. Okay, so let's go. What we have is that, okay, F0 applied to x0, right, is capital F applied to x0, 0. So since capital F is continuous, this is the limit when n tends to infinity of capital F applied to xn Tn, right? But this is the limit when n n tends to infinity of ftn applied to xn, and we know that this image is equal to the image by ftn of yn. So we have this equality over here, but this is equal to the limit when n goes to infinity of capital F applied to yn tn, right? And this is capital F applied to the limit when n goes to infinity of yn tn, again by continuity of capital F, and we get capital F of y0, 0, which is f0 applied to y0. But f0 was an embedding, it's an embedding. And so in particular, f0 is injective. So that implies that x0 is equal to y0, because f0 is an embedding. Okay, and now we have a problem, because the map capital F hat applied to xn tn is equal to the map capital F hat applied to yn tn, because this map is essentially F and we just add tn to the end. So we have this, and these 2 points, xn tn and yn tn, are different. And these points converge to the point x0, 0, right? Because this point converges to x0, 0, and yn tn converges to y0, 0, but y0 is equal to x0. So in particular, what we get is that this equality and and the fact that x0, 0 is the limit when n goes to infinity of xn tn, and also the limit when n goes to infinity of yn tn, implies that capital F hat is not injective in the neighborhood of x0, 0. Indeed, it's not injective in any neighborhood of x0, 0. But this contradicts what we proved. We proved that capital F hat is injective in a neighborhood of any point of the form x0. So in this way, we obtain a contradiction. And so the property of being an embedding is actually also stable. Let us show that the property of being a diffeomorphism is also stable. Okay, so assume for a second that we have a differentiable map from M to N that is a diffeomorphism. Okay, and M is compact. So in particular, we can consider the connected components of M. And since M is compact, it has finitely many connected components. Okay? Of course, now we can define Nj as the image of Mj, and that's going to be a connected component of N, because F0 is a diffeomorphism. So we get in this way n1, n2 till nk, which are the connected components of the manifold N. And what happens is that if we consider how homotopy and we perturb F0 a little bit, what's going to happen is that Ft of Mj is going to be contained in Nj for all j bigger or equal than 1 and smaller or equal than k, and t close to 0. So in order to show that F0 is a diffeomorphism, that Ft is a diffeomorphism for t close to 0, we can restrict ourselves to the connected components of M. Okay? So we can assume that M is connected because it suffices to work in any connected component of M. It's just that simple. Good. So we're now in a situation in which we want to prove that being a diffeomorphism is a stable property. And what we want to see is that on the one hand, we want to compare diffeomorphisms, and on the other hand, we want to compare them with local diffeomorphisms that are submersions. Okay? It is clear that a diffeomorphism is a local diffeomorphism, which is also a submersion. So the implication from left to right is fairly simple. But what happens from right to left, at least in our case, in which our manifold M is compact? Okay, so of course here we have to add something else, because local diffeomorphism plus submersion is not going to imply that it is injective. So we can add here that that it is also an embedding. But it's still true. A diffeomorphism is a local diffeomorphism, which is also it's also submersion, and it's also an embedding. So the implication from left to right does not create any trouble for us. Now, suppose that we are in this situation in which we have f from M to N that satisfies actually all these properties. It is a local diffeomorphism, it is also a submersion, and finally it is also an embedding. Okay, let's assume that all the three properties are satisfied. What happens is that on the one hand, the image of M is an open set. And why is that? Because that's a property of submersions. If you want, it can be deduced from the local normal form of submersions. So we have this for submersions. But we know also that M is compact. And the image of a compact set by a continuous map, it's still compact. But compact set is closed, so we get that the image of M is closed. And now we have that the image of M is an open and closed subset of N. And N is connected because F is a diffeomorphism from M to N, and M is connected. So N is connected too. In particular, that implies that the image of N is the whole N, right? And now we're in a situation in which F is a local diffeomorphism, which is surjective, and it is also injective because it is an embedding. So it's a diffeomorphism. Okay? So what we actually prove is that here, in our case, when M is compact, being a diffeomorphism is the same that being a local diffeomorphism, which is also a submersion, and it is also an embedding. But all the properties to the right are stable. Being a local diffeomorphism is stable, being a submersion is stable, and being an embedding is stable. So being a diffeomorphism is also stable, okay? Since all the properties to the right are stable, the property to the left is also stable. And so we get that being a diffeomorphism is also a stable property. In this lecture, we consider stable properties. In a simple case, when we are actually working with differentiable maps such that the source space is compact. But we are not just concerned with the stability, we are concerned with knowing when the properties that we are considering are dense. When we can, therefore, we can perturb a little bit a map and transform this map into a map that has much nicer properties. For instance, being a submersion or an immersion or an embedding. And that's the kind of thing that we are going to study in the next lecture. We are going to introduce the tools that are going to be necessary to show the first version that we are going to see of the Whitney embedding theorem. Thank you for your attention.